Let's be real for a second. Real-world data is almost never a nice, neat, simple, straight line. So how do you possibly model these complex, nonlinear patterns without your model going totally off the rails? Well, in this explainer, we're going to pull back the curtain on one of the most elegant solutions out there, splines.
And this right here is the core problem, isn't it? You try a simple linear model and you miss all the important details. But then you try some high-degree polynomial, and you get this crazy oscillating curve that's basically just memorizing the noise, not finding the signal. We need something better. We need a tool that's flexible enough to see what's happening locally, but smooth enough to be, believable.
To really appreciate why splines are so genius, we first have to understand why the usual suspects just don't cut it. And this brings us to what I like to call the modeler's dilemma.
So you're basically stuck between two pretty bad options. On one hand, you've got polynomial regression. It's smooth, sure, but it's a global model. That means one weird little area of your data can have a massive, crazy influence on the entire curve, way over on the other side. On the other hand, you've got step functions. These are great at capturing local trends, but look at the result. It's this clunky, jagged, totally unnatural-looking fit. We need the best of both worlds, and right now we have neither.
So where does the answer come from? Well, this is the cool part. It doesn't come from some hyper-modern computer science paper. The inspiration is actually a centuries-old physical tool from the world of shipbuilding.
I want you to picture this. A long, thin, really flexible piece of wood. Back in the day, shipbuilders would lay it out, pin it down at a few key points on their blueprints, and the wood itself would naturally bend to create a perfectly smooth curve between those pins. This physical tool, this is the perfect mental model for what we want our algorithm to do.
So how do we translate that elegant wooden strip into cold, hard math? Well, with this idea, the piecewise polynomial. Instead of trying to fit one super complex polynomial across all the data at once, we're going to fit several much simpler, low-degree polynomials over different sections or pieces of the data.
And what about those pins that held the wooden strip in place? What's the mathematical version of those? We call them knots. These knots are just the specific points where one of our simple polynomial pieces ends and the next one begins. And just like with the wooden strip, the more knots we add, the more flexible and curvy our line can become.
All right, enough theory. Let's see how this thing actually works in practice. We're going to apply this piecewise idea to a real data set, trying to model how a person's wage changes with their age.
So here's our game plan. It seems simple enough. We'll fit one cubic polynomial for everybody under 50 and a totally separate cubic polynomial for everyone 50 and older. Our one and only knot is right there at age 50. Easy, right? What could possibly go wrong?
Oh yeah, that can go wrong. See, because we fit those two curves completely independently, there's absolutely nothing telling them they have to meet up. And the result is this awful, jarring jump right at our knot. This is not the beautiful, smooth curve the shipbuilders promised us.
Okay, that jump is a total deal breaker. We can't just let our little polynomial pieces do whatever they want in their own little sections. We have to force them to connect, and not just connect, but connect in a smooth, continuous way. So how do we fix it? How do we get rid of that ugly jump? It's actually pretty straightforward. We add rules. We're going to mathematically force these two curves to talk to each other by imposing some constraints on our model. We're going to do this in 3 key steps. First, the most obvious one. We tell the model the two curves have to actually meet at the knot. No more jump. That's continuity. Second, we force their slops, their rate of change, their first derivative, to be exactly the same at the knot. This gets rid of any sharp, pointy corners. And third, for that ultimate buttery smoothness, we also force their curvature, their second derivatives, to match up perfectly.
And when you take our original idea, a piecewise cubic polynomial, and you apply all 3 of those constraints, you get something really special. It now has a new name. It's officially a cubic spline. It is literally engineered for smoothness.
And would you look at that? Here is the result. It's the exact same data, the exact same knot at age 50. But now, with our smoothing constraints in place, we get this beautiful, continuous, and perfectly smooth curve. This is the power of a spline. You know what's really great about this? Controlling the spline's flexibility is incredibly simple. The degrees of freedom, which is just a fancy way of saying how wiggly the curve is allowed to be, is simply 4 plus k, where k is the number of knots you decide to use. You want a more flexible curve? Just add more knots. It's that easy. Okay, so now we've totally mastered the classic cubic spline, but the rabbit hole goes a little deeper. Let's take a quick look at a couple of powerful variations that are designed to solve some very specific problems.
So a regular spline can sometimes get a little wild and wacky at the very edges of your data. A natural spline fixes this by adding one more rule. It forces the curve to become a straight line beyond the first and last knots, which makes it much more stable. Then there's the smoothing spline. This thing takes a totally radical approach. It says, forget choosing where to put knots, let's just put a knot at every single data point. And it controls the absolute chaos that would cause by adding a penalty that punishes wiggliness.
Now this formula looks a bit scary, but the idea is pure genius. It's a trade-off. It's a tug of war. This first term here wants to fit the data perfectly. It wants to touch every single point. But this second term, the penalty term, wants the curve to be as smooth as possible. Ideally, a perfectly flat line. And this little lambda here, that's the referee. It controls the balance between these two competing goals.
So why does any of this really matter? I mean, splines are a really clever way to draw curves, for sure, but they're also something more. They are the fundamental building blocks for one of the most powerful and, importantly, interpretable models in all of modern machine learning.
And that powerful class of models is the generalized additive model, or GAM for short. You can think of splines as the secret ingredient that gives GAMs their incredible flexibility and power.
So this is what a GAM formula looks like. At first glance, it kind of looks like a regular linear model, right? But look closer. Instead of just having simple coefficients for each variable, we have these flexible functions, f1, f2, and so on. And what do we use for those super flexible f functions? You guessed it. Each one of them is a spline.
And this is a total game changer. With GAMs, we can use splines to model the complex nonlinear effect of each variable separately, all inside one additive model. We get all the flexibility we need to capture really complex patterns, but because we can still look at the shape of each individual spline, the model doesn't become a black box. It's this beautiful compromise between raw power and human clarity.
So, in the end, splines give us this incredible tool, this way to build a complex, beautiful whole out of simple, connected pieces. It's a powerful idea that blends being able to adapt locally with maintaining a smooth overall structure. And it really makes you wonder, right? Where else, in data, in design, maybe even in how we think, could this piecewise approach help us find that perfect curve?